surface of the moon, sort of dry, barren, uninhabitable. And the Earth is very different, right? We all know this. It's got water, it has life, it has plate tectonics, it has a strong magnetic field that we think is important for protecting life at the surface. And so for the rest of the talk now, I'm going to be zooming in into the Earth's deep interior. This cartoon, there we go. This is sort of a cartoon just diagramming the rocky mantle, the liquid iron outer core, and the solid iron inner core. Okay, so first question, what is the inner core? The inner core is this solid mass of iron, mostly iron, with some other elements mixed into it, situated at the very center of the planet. And outside of it is a large layer of liquid iron, convecting. And it's that liquid iron that's generating the magnetic field. I'll go into it in a bit more detail. And above that is a much lower density material. These are silicate rocks in the mantle that convect over very long time scales, much slower than the core. And of course, at the surface, we have oceanic plates subducting down into the mantle and new crust being created at mid-ocean ridges. And to give you some perspective, here's this inner core. This is, of course, not a photo. We don't have any photos of the deep interior. Can't see there, but we do know the conditions are extreme. So the pressures are well over 300 gigapascals. That's 10 to the 9 or a billion pascals. The temperatures somewhere between 5,500 and 6,000 Kelvin is similar to the temperature at the surface of the sun. So it's the hottest point in the planet. It's the highest pressure point. So it's the most extreme place in the planet. And just to give you a sense of size, it's a little bit smaller than our moon. So it's small, but it's not that small, right? It's still kind of like a little planet in the middle of the planet, middle of the Earth. Okay, so here's the big picture to motivate you for the talk tonight. Much of my research is driven by answering this first question. How is Earth cooled over time? Because this determines why we have a habitable environment. The interior is central to maintaining a habitable surface over billions of years. And if we want to understand rocky planets, exoplanets in general, and look for the next Earth, we need to be able to answer this first question. And answering this first question, of course, is a geological question. So to get at it tonight, I'm going to look at when the inner core formed. I'm going to refer to the inner core often as IC. So if you see IC, that's what I mean. Is there evidence for when we think the inner core formed? And of course, this is going to be in the form of magnetic evidence. And what are the implications of that? In the last couple of slides, I'll talk about what this might mean for the rest of the Earth. So who cares? So the inner core age, as I just told you, gives us a temperature at a time in the Earth's history. So this is a really valuable data point. It gives us the temperature at the center of the planet at radius of 0 at a time, assuming we can pin it down, which would really help anchor all of our thermal evolution modeling of the Earth. And some of the more technical points I'll get into tonight is driving the magnetic field over 4.5 billion years, which we think the magnetic field is that old. If the inner core is old, that implies the magnetic field, or geodynamo, has been driven mainly by the inner core growing slowly over time, releasing convection and energy. But if the inner core is young, say it's a couple 100 million years old, that's what I mean by young, that implies that most of the Earth's lifetime, the geodynamo is driven by just thermal cooling with no inner core. Okay, so to motivate, the reason why we care about the magnetic field, of course, is that it provides this nice magnetic shield for protecting the Earth from harmful, to life at least, these high energy solar particles. Of course, this sketch is not to scale. The Earth is much farther away from the sun than depicted here, but you get the idea. There are storms on the sun that release high energy particles. And when they hit the tip of the Earth's magnetosphere here, this bubble shoots those particles away from the Earth and downstream towards Mars. And so we're protected from a lot of that radiation. There is some radiation that sneaks through near the poles where the dipolar field lines intersect the Earth's surface. And this is where you see those visible aurorae if you're at high latitudes near the poles. Okay, so here's the outline for the rest of the talk. I'm going to talk a little bit about inner core basics, what we know about the inner core. Then I'm going to go into the paleomagnetic rock record, what it looks like. And then I'm going to go into the dynamo modeling and explain and show to you why we need to do these kind of more complicated models to really get at the heart of this problem. Okay, so inner core basics. So here is a profile of the structure of the Earth as constructed by many, many different earthquakes. This is called PREM, preliminary Earth model. It's not so preliminary anymore. But here's the density profile, the solid line, and VP and VS. VS is a shear wave, and shear waves cannot be passed through a liquid. And we see the shear wave velocity go to 0 in the outer core, and it goes back up to some finite number in the inner core. So this was the first dead giveaway about 100 years ago, that the outer core is liquid and the inner core is solid. And this big density jump here, this solid black line, tells you something about the material. And we now know that, of course, this is silicate rocks here in the mantle, and then a very sharp jump at this core mantle boundary to liquid iron. So about a factor of 2 increase in density there. And of course, as I mentioned earlier, it's in this liquid outer core that is where the dynamo is generated. Okay, so how do we think the inner core formed? Well, there are 2 lines of thought, and I'm only going to explore the second one here, but I thought I would do it justice by introducing both of them. So there is an idea that the inner core could have been inherited somehow, could have snuck into the core during a cold accretion scenario, where maybe there wasn't much heat deposited during accretion. We have this primordial solid iron body snuck in there. It wasn't solid. There's some evidence supporting this, such as most of the impact heating is concentrated in the outer part of the planet, so the impact heating actually doesn't heat the interior too much. And there's also a problem with nucleating iron at high temperature and pressure. But I don't think these are big barriers. I think they're kind of caveats. And the more likely scenario is scenario 2 here, that there was so much energy available during formation. The whole planet was liquid, certainly after formation. And this little equation here just shows you, for a planet with the radius of the Earth, you get about 40,000 Kelvin or 40,000 Celsius, depending what scale you use, which is plenty enough temperature to melt the entire planet about 10 times over. So there's plenty of energy available to melt the planet. So we're going to go with this hot scenario. It's sort of the mainstream idea. So to give you some idea, of course, our Earth started, we think, in a magma ocean stage. The whole planet's liquid. And then over time, it just cools down slowly, fast at first and more slowly towards the end, perhaps. And at some point, this liquid core, iron core, started to solidify. And the inner core has been growing ever since. And then one other point I want to make on this slide is geologists sometimes go forward in time, from time 0 to time present day. That's 4.5 GYR, that's billion years, 4.5 billion years. And sometimes they like to go backwards. So they say GA, sorry, that's billion years ago. The present day is 0 GA. And then formation of the Earth is at 4.5 GA. So I just wanted to point that out, because some of the plots I'm going to show are going to switch. So here's a diagram of Earth's history, some of the seminal events in Earth's history that you might be more familiar with. For example, the formation, core formation, some of the oldest rocks, when we think the moon formed about 50 million years after the Earth formed, some of the oldest sedimentary rocks, some isotopic evidence for life 3.9, 3.8 billion years ago, some actual fossils, 3.5, more fossils, rise in atmospheric oxygen, hard shell mammals. Actually, we're going to come back to this at the very end of the talk. There was a move out of the ocean onto land during the Cambrian explosion and in the Ediacaran about 700 million years ago. And then, of course, dinosaurs and humans are a tiny little sliver here at the end. But what's missing from this is anything to do with what's really going on in the interior. And I think putting inner core formation on this chart would be a real advance in understanding how the planet has evolved. So that's my goal here tonight. Okay, so how does the inner core grow over time? Why does it grow? Why doesn't it solidify from the top down, for example? And here's a diagram showing you why we think it solidifies from the middle out. Here is a temperature. I'm showing you here temperature as a function of radius, and 0 radius is the center of the planet. CMB is the core mantle boundary. So here's the top of the iron core. And say the temperature profile when the Earth formed was this black line. Okay, I intentionally have no numbers here. This is a conceptual plot. And then the material in the core, which is mostly iron, has some characteristic melting temperature that increases with pressure. So it's harder to melt at depth, is what that means. And as the planet cools, you can imagine as heat is lost through to the mantle and out into space, this temperature profile in the core is going to drop slowly. And when it starts to intersect the iron solidus, you're going to start to solidify iron where the temperature is beneath this curve. So on the bottom part here, you'll have solid. So here you have an inner core that's grown out to about here, this dashed line. And the outer part is still liquid. And as you cool the core even more, it'll just keep growing until you get to the present day inner core size. So that's the basic idea of how the inner core grew. Get rid of this bar. And here it is from a sort of pulling back a little further. Now here's the radius of the whole planet. Here's the center of the Earth. Here's the surface. And I'm showing you here, the red is the solidus again for iron, the melting curve. And the black is, say, the temperature, initial temperature of the Earth. So it's all above the liquidus. It's all liquid. And eventually cools down to this blue curve. And we intersect the solidus at just the right radius, at the correct inner core radius, which we know from seismology today. And I should say that the cooling, see these curves are very close to each other. So you only need to cool the core by about 50 degrees to get the inner core to go from 0 radius to its present day radius. In other words, you could heat it up today by 50 degrees, the whole core, that inner core would liquefy and completely liquid, okay? So it's not a lot of cooling. It's pretty subtle. And the way that I model this cooling, how you go from this black curve down to this blue curve over time, is by looking at the energy balance over the whole planet. So I think about how energy is lost to space. What are the heat sources in the mantle? There's some radiogenic heat. This is the decay of some particular elements that release heat in the mantle and in the core. Some heat that's lost from the core, and eventually heat that's lost from the inner core. And to do this kind of modeling, this is called thermal evolution modeling, okay? And it gives you these solutions of temperature and the mantle core, inner core radius, and maybe the magnetic field strength, if you have a good scaling law. So in order to do this thermal evolution model, though, you need to know some constraints about how fast the Earth is losing heat today. And so here I'm showing you the Earth's heat budget. On the right, this table is a breakdown of the heat budget. There's about 46 terawatts. That's 10 to the 12 watts of heat being lost to space right now out of the solid Earth into the atmosphere. Of course, the heat going through the atmosphere is about 1,000 times this. So the atmosphere does not feel this cooling. It's tiny. Neither do we, for that matter. But for the Earth, this is the primary source of a loss of heat. 46 terawatts. Most of this is lost through the oceanic crust. So what's literally under the oceans. And you can see here by this heat map, most of the heat is being lost in the oceans. And that's because that's where the crust of the mantle is the thinnest. It's being created here at these ridges, where it's red, these mid-oceanic ridges here in the Atlantic and in the Eastern Pacific. And then where the plates subduct beneath the continents, and you have very thick cold crust like beneath our feet today, we have very weak, slow diffusion of heat out of the mantle. The important thing we need to know today is what's the breakdown in terms of heat flowing through the mantle. And to the best of our knowledge, we think that of the 39 terawatts coming out of the mantle, a third is the temperature drop in the mantle itself, that's secular cooling. A third is radiogenic heat production by radiogenic decay. And a third is coming out of the core. So it's just the mantle's drawing heat out of the core at whatever rate it wants to, depending on its material properties. So I'm not sure it's just a coincidence. These are all a third, but this tends to be what the sophisticated models tell us and the observations. Okay, so putting all that all together, back in 2014, we published a thermal evolution of the core that met all of these constraints to the best of our knowledge. So this is sort of one nominal solution. I put it here in a frame because thermal evolution modeling is almost as much as an art as it is a science. People do not agree on what this thermal evolution is. There's too many poorly constrained properties here, and the physics is not known well enough. But this does meet all of the observational constraints, and I think it's a step forward. And this modeling gives us an age of inner core formation. And that age we found in 2014 was 650 million years ago. Okay, so before that Cambrian explosion, less than 1 billion years old. So in geologic terms, when I published this, people said, "Oh, is that young?" People think this is young. So this is very young for a geological thing. And then I'll just say the update more recently is about the same number, 627. The uncertainty on this number is pretty large, plus or minus 50 to 100 million years even. Okay, so these are kind of rough numbers. Keep that in mind. Okay, and then in the same paper, or from the same model, I used a magnetic scaling law to take the core temperature decrease over time and map it into a magnetic field intensity, this black solid line, over 4.5 billion years. So now I've switched to a GA scale. So this is present day at 0 GA, and times 0, or 4.5 is when the Earth formed. So this cooling history predicts this magnetic field history. And this axis is in these funny dipole moment units. Don't worry what the numbers are, but the present day field strength is about 50 in these units. And so my scaling law gets the right present day field strength, but it doesn't match these data intensity. That's what these circles here are. They're measurements from rocks. And I'll get into much more detail on that in a minute. And here's the inner core radius here, growing at 650 million years and growing to its present day size of about 1221 kilometers today. Okay, so I meet all the constraints, except I was never happy with this fit. You know, that obviously the magnetic scaling law does not do a good job at explaining the data, or there's something wrong with the data, or possibly both is in fact what I'm going to show you. Okay, so I wasn't the only one to make this kind of prediction. Here's a number of my colleagues made similar predictions. So back in 2003, Labrosse pointed out, oh, there's a big gap in the record. Maybe there's something going on here. Labrosse, Julien Aubert didn't have a good constraint on the age of the inner core. You see that's where these little bumps are here. And these black dots are paleo intensities, magnetic field intensities measured from rocks back in time. So his constraints were not great. They were either, maybe 2 or maybe 500 million years ago. Again, this is the plot I just showed you in 2014, which actually pushed the inner core quite young. This was the first model that had the inner core argued for definitively around 600 million years. And then some later papers by Nimmo, for example, I got similar result to me about 500, 600 million years ago. And then a paper appeared in Nature in 2015 that argued that this jump in paleo intensities right here may be associated with the inner core nucleation. And again, my time axes are flipped depending on which plot you're looking at. So in this plot, this is back at formation, and this is going forward in time, and then the inner core would nucleate here and maybe bump up. But these data points right here were then quickly called into question, and they don't seem to be valid, all these data points right here. So I'm not going to go into that to detail today, but people don't think that's the picture right now. Suffice to say, the range of the inner core age is huge. It could be between 0.4 and 3 billion years old, right? Huge range. Totally unacceptable, really, from an evolution standpoint. Okay, so let's try and get at this problem with some more data. I'm going to explain where those data points come from now. So as I mentioned, the magnetic field is generated in the liquid outer core by a dynamo, where you have electrically conducting fluid convecting. These little electric currents generate a large-scale magnetic field, and it's got to be maintained over time. And what we're going to be looking at in this section is some of the observations. So magnetic directions, that's how these magnetic field lines are oriented on the Earth's surface. As Alicia showed you today, here they are not perfectly aligned with our rotation axis. They're slightly deviated. And Carnegie and Louis Bauer and people 100 years ago knew this, and that's why they put those ships, they sailed those ships around the oceans to map out the Earth's magnetic field over the oceans for navigational reasons, but also for scientific curiosity of why is the field changing over time. So these directions are going to change over time at different places, and the intensity or the strength of the magnetic field is going to change over time. And we call that paleointensity because it's locked up in rocks. So here's roughly how the recording works in rocks. You have a rock that's made up of, say, some non-magnetic minerals and some magnetic minerals. The gray are the magnetic minerals. This is typically magnetite, which is full of iron. And when the rock is very hot, these magnetic carriers are randomly oriented just from thermal excitation. Even if you have a strong ambient magnetic field in its presence, they will not align when they're hot. They're above the so-called Curie temperature. But as you cool the rock down, if the rock, say, is a volcanic eruption, it'll cool at the surface, and the magnetite will align itself with the ambient magnetic field at the time, and will stay this way as long as the rock doesn't get perturbed, doesn't get heated up, doesn't get struck by lightning, nothing like that. Then you have a nice pristine rock. And of course, the direction and the magnitude of these little vectors in the rock will correlate with the ambient magnetic field at the time. Okay, so it's sort of like a little timepiece telling you what the field looked like at that location on the surface of the Earth. Now, just from the geometry of a dipole, where you have magnetic field lines coming out the southern hemisphere, looping up into space and going back into the northern hemisphere, you can imagine where you are on the Earth matters for this orientation. If you're at the poles, you measure a vertical magnetic field in your rock. If you're at equatorial latitudes, you measure a horizontal. Imagine standing on the Earth here, these would look horizontal, right, to your orientation. So the direction of these little dipoles in the rock tells you something about your latitude. Okay, that's key. That was one of the founding principles of geology back 60, 70 years ago. So here's what the Earth's magnetic field looks like over the last 10,000 years, to give you some sense of how much it actually changes. You're looking at intensity here for different in the color bar, but also different signs. So it's negative intensity and positive intensity. So you get the vector as well. So in the northern hemisphere, it's mostly negative, pointing inwards. Southern hemisphere, mostly positive, pointing outwards. But and this black line here is the magnetic equator, where you go from positive to negative. And you can see it wiggles, right? It's not static. It changes constantly. And here's just another example of that. And this is actually from a movie, from a model of mine, where you see the movie here of the magnetic field at the surface, kind of wiggling and changing over time. And the time average looks like almost a perfect dipole, where you have blue in one hemisphere, red in the other. And the equatorial equator, the magnetic equator is aligned with the actual equator. And when you have a time average that looks this perfectly dipolar, you call it a GAD field. This is some jargon, but it's important. This is known as a geocentric axial dipole. So geocentric meaning that it's as if there was a very strong dipole placed right in the center of the Earth, and it's aligned with the rotation axis, and it's a pure dipole, no other harmonics. So the idea is that you will always see a GAD field on the Earth if you average over long times. So either your rock cools over 1 million years, or you have a sequence of rocks that all cool next to each other over the course of 1 million years. And if you sample them correctly, you should average out everything that's not the GAD field. You'll just see the GAD field. On the other hand, if you don't have a GAD field, then the field is going to be tilted with respect to the rotation axis. And that would be, for example, a non-GAD field. And as we know, the actual magnetic pole of the Earth is somewhere over Siberia today, and it's tilted about 11 degrees compared to the rotation axis. And here you can see over the last several hundred years, it's been wandering. It has no direction. It just kind of wanders. It's kind of like a weather pattern. And that's kind of what's driving it, is these big vortices in the core of liquid iron generating this magnetic field, constantly changing, okay? So when we look in the rock record, we see what look like changes in the magnetic field. It looks like the inclination in one location is changing. So for example, here in North America, if you look back in time, the magnetic inclination will be changing over time. And there's at least 3 ways to interpret that change in magnetic inclination. The first is that you assume a GAD field, and that means the magnetic pole is aligned with the rotation axis, which implies that if your inclination is changing, your continent is wandering. right? And this was some of the first evidence for continental wander or continental plate tectonics back in before World War II. Is they see these wandering continents and they say, well, that's weird. What's going on there? Of course, there's another interpretation. It could be that your continent is fixed in place and it's the magnetic pole that's wandering. And I just showed you that happens. We know that happens. So whether you're in this scenario here or this scenario is unknown. That's something you need to tease out of the data and do a bunch of modeling. The third possibility, which is a bit more extreme, is that the Earth's entire crust may rotate on its side. This is called true polar wander. And people do think they see this in the rock record, where all the continents simultaneously rotate. Not to this dramatic extent, but a little bit, a couple degrees here or there. Okay, so that's called true polar wander. Okay, so here's the magnetic field intensity. This is the latest compilation we put together back in 2018. Whoops, go back. Too many animations. Okay, so each dot here is a paleo intensity measurement. The unfilled white circles here are ones that have been thrown out because the data was bad, the magnetic techniques in the lab were bad. And I'm showing you here in gray a time average of this data. Okay, so it kind of wiggles, 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 wiggles. And then in present day, the last 500 million years, we really have a lot more data. And that's just because preservation bias, right? We just have a lot more newer rocks. And you can see that from the histogram here at the top. But two important takeaways from this, just looking at the data right here. First is that the present day intensities here, okay, I show it in this flat line, is that the wiggling gray line doesn't deviate much, right? My interpretation here is it's flat. It's sort of, magnetic field intensity over the last 2 billion years is just kind of wiggling around the present day field intensity, which is a bit odd. Because as I just showed you, the Earth should be cooling significantly over this 2 billion years. So there's something strange there. The second thing I'll point out is this gap. There's a very long gap in the data. There's a lot of missing intensities right in here. And this is called the Neoproterozoic. Between 550 and 950 or 980 million years ago, this era is called the Neoproterozoic. Lots of interesting things are happening. Lots of things are evolving in the ocean. Life is coming out onto land. But for some reason, there is a real dearth of magnetic data. And I went and asked the paleomagnetists why. They say they don't know. Okay, they say there are rocks of this age. They don't know why there's data missing there. So just to overlay my 1D prediction from back in 2014 is this blue line. I would say this typically just doesn't really agree. Okay, maybe this flat bit here agrees. We don't see this. We don't see this dip right before inner core nucleation, predicted at 600 million. And we don't see this trend of this cooling of the planet. So at this point, I would say we have a murky picture. It's not clear what is going on. There's some contrasting things. There's no clear signature of inner core nucleation. Why is the paleointensity record so flat? Why is there a sparsity right in this Neoproterozoic period when I predicted the inner core to have formed? And why is the paleogeography unsettled? I didn't get into this. Whoa, I meant to do the pointer on that one. I didn't get into this last bubble here, but there is some of the continental motions around this time are kind of weird. And I will show you a little bit of this at the end. Okay, so this takes us to the final part, which is about what is generating the magnetic field and what could be going on in the core at this time. So first things first, let's define a dynamo. A planetary dynamo is a system that generates a magnetic field through fluid motion and induction. And the magnetic field at all times is trying to just decay away into space. So you need to supply some energy to concentrate it and to constantly induce that field in the core. Okay, so there must be something going on in the core to generate this field constantly. It's not just a big magnet. There's 3 ingredients you need for a planetary dynamo. The first is planetary rotation, which is a bit trivial because everything rotates basically in the universe. It's easy to rotate. So just some rotation. You need a large electrically conducting fluid in your interior. So by electrically conducting, I mean metal. Okay, So metal, we typically think of metals as like iron and steel, which is good. So in the Earth's core, we have iron, liquid iron. So we got that check. But I'll just mention here that in other planets like Jupiter, the dynamo is generated not in liquid iron, but in metal hydrogen. So at high pressures and temperatures, other atoms like hydrogen can become metals. And that just means there's a free electron floating around. So you pass a charge through them and they react. They all react in concert, right? Okay, so the first two are actually fairly common. Everything rotates. Every planet in the solar system has a large electrically conducting fluid, believe it or not, in its interior. And I just say every planet in the solar system has a magnetic field or had one in the past, except maybe Venus. Venus is the one outlier. And you can go back to my talk from a couple of years ago if you want to see more about that. Okay, but third, and the hardest thing, is this energy supply. We need some energy to make sure the fluid is constantly moving, convecting in the core, in the liquid outer core. And by convection, I mean something that's generating buoyancy at its base such that it wants to rise. So for example, when you boil water, you put heat at the base. The water heats up at the base, it expands. And when it expands, it wants to rise and go to neutral buoyancy. But you got to continuously do that. So you basically need this continuous heat source or energy source to drive that convection. And here's a nice conceptual laboratory experiment that my PhD advisor drew up and then I borrowed from him. Is imagine you're in a laboratory, and of course this is not actually possible, but maybe if you had infinite resources you could do this, because you need a tank of metal, liquid metal, which is very hard at room temperatures, of course. But if you did have a tank of liquid metal, you would put it on a turntable and spin it at some angular velocity big omega. You would have an ambient magnetic field, B naught, in the laboratory that you supply, and later we'll take away. But for now, you supply it. And initially, you just spin the whole thing up. Step two is to put a propeller in there and counter stir it in the opposite direction. So now you're really driving convective motions, swirling in this iron, in this liquid metal. And what that will do is it'll induce new magnetic field lines that will add on to the ambient field, okay? And then the third critical step is to remove the ambient magnetic field B naught. Oh, I should have removed it there. Turn off your laboratory magnet, but keep spinning the tabletop and keep spinning that propeller. So you keep all the convection going and the rotation going. So there's two possible outcomes here. The first is a negative one. It's that over some time, the magnetic field you induced B1 just decays away, and you're left with just a non-magnetic fluid that's just convecting and rotating. It's doing nice, pretty things, but it's not a dynamo. It did not generate a magnetic field. The other possibility is that you did stir that propeller fast enough, or you were spinning the tank, or it was electrically conducting enough to maintain this secondary field B1, even though you no longer have your ambient magnetic field B naught. So in this case, you do have a dynamo. So you're generating a magnetic field from convecting electrically conducting fluid. Okay, this has been done in some experimental settings, but they're not this simple. They're usually long tubes with big propeller systems through them, and they're closer to plasma than they are to liquid metals. But nevertheless, there's a special dynamo parameter called the magnetic Reynolds number, that it's the fluid velocity times the shell thickness of your tank over the magnetic diffusivity. And if this magic number is above about 40, then you're expecting to have a dynamo. It's just very hard to reach this number in the laboratory. Okay, so what about the energy source? So there's three regimes I like to think about that the core could be in. You could have a thermally convecting core, which is like this analogy of boiling water, where the core is much hotter than the mantle, and heat is just being drawn out of the core fast enough to drive fluid motion. You can kind of think of it as cold blobs of liquid iron will be sinking back down into the core. Because up here at the top of the core, they're getting cooled rapidly. And the rest of the core is just very hot. So you're like dropping ice cubes down into, or ice is a bad example because it's buoyant, but dropping cold liquid iron back down into the core. Compositional convection is when the inner core starts growing. As the inner core grows, that solid iron matrix that is the inner core doesn't want any impurities. It doesn't want hydrogen or carbon or sulfur or silicon. So any of those light elements, which we know must be in the core from its density, are going to get rejected right at this boundary, this solidification boundary. And when they're rejected right there, they become like a low density fluid, just like the water at the base of your pot. So this is called compositional convection. And we actually think this is the dominant buoyancy force in the Earth's core today. And of course, you could have a combination of the two. So you could have thermochemical convection. And I want to get to my one last conceptual slide to give you some larger intuition about how these magnetic fields evolve over time. And I've given it this kind of silly name of a Goldilocks cooling rate, because I haven't thought of a better name. But the idea is that the cooling rate of the planet, of the core, is really what's critical here. You don't want it cooling too slow or too fast. You kind of want it right in the middle. Okay. So here's what happens. If you have a slow cooling core, the magnetic field may start off quite strong because your planet's very hot, and you'll have thermal convection for a little bit. And eventually that thermal convection will just weaken. And because the core is cooling very slowly, you're not drawing all that heat out. You're not driving convection. So the convection will just stop and your dynamo will just die eventually. And I propose that this is probably what happened on Venus and on Mars, where we know it did have a magnetic field 4 billion years ago, and then it suddenly died. We don't know why. Then in the middle case, you have a moderate core cooling rate where you have a thermal cooling initially, and then at some point along the line, your inner core nucleates, and you get this big boost of convection from that rejection of those light elements from the inner core. And that big boost will give you what we think will be like a bump in the magnetic field strength. And this is a very good way to keep a magnetic field alive for billions of years, because you've got both the thermal and the compositional convection. And in this category, I would put Mercury, Earth, and Ganymede. Mercury and Ganymede both have dynamos today. They're tiny little rocky planets. Well, Ganymede's a moon. But we think that this is what's going on in their core. They have an inner core that's crystallizing, and we think the magnetic fields are ancient. And then on the fast cooling time scale, you can imagine just putting everything on fast forward. So if you cool very quickly, you go through your thermal phase quickly, the inner core nucleates early, and then maybe the whole core solidifies out because you take so much heat out of the core, the whole core is subsolidus. It's the whole thing is solid. And of course, if you have a solid ball of iron, it's not going to convect. It's not going to generate a magnetic field. So you're dead. You're done. And there's some evidence to support the moon's paleomagnetic record looks like it's died and then bumped up and then died again. So I put the moon in this category. And I would suspect Psyche, which is this small asteroid that NASA is sending a probe to, may have suffered a similar fate. And soon we'll have some magnetic data from the surface of Psyche. We can test this prediction. And then, of course, my daughters had to make their own interpretations of the Goldilocks cooling rate. So you can interpret that how you will. Okay, so here's the big idea. Getting back to the big idea. Let's try and take a step forward. We've got this 1D cooling, but it doesn't really solve the problems we're looking for. So what I did back in 2016 was I took this 1D model and I used it as a boundary condition on a 3D dynamo model. So it sounds easy in principle, but to actually get these evolving boundary conditions right takes a little bit of trickery to make sure that you're evolving, that you land at the correct present day state from 2 billion years ago. That's the goal. So you're evolving forward, but you only know the present day state. So you have to scale these boundary conditions to meet that condition. So what I'm going to do is I'm going to evolve a numerical dynamo model from 2 billion years ago to the present day state with the idea that somewhere in there the inner core is going to nucleate. And here's just a snapshot of what one of these models look like. It's a numerical dynamo model. It's in a spherical shell. So this is the liquid outer core I'm modeling here. So this is the core mantle boundary, the outer boundary here. And then here, this inner sphere is the inner core. I don't model what's going on in the inner core because it's solid. I'm just modeling the liquid convection in the outer core. And to do this, we couple set of 4 equations together and solve for the velocity, the pressure, the temperature, the magnetic field intensity. All of these equations are well known. But it's actually it's a numerical challenge to solve these equations over the whole sphere of the outer core and resolve all the small scale convection we think is going on. It's a very small scale because the viscosity of liquid iron is like water. It's like liquid water. So the scales we think are meter scale little eddies in the outer core. So you really need to push down to extreme conditions to model these things correctly. Okay, so here's the main result. This is it. This is the dipole moment intensity. Again, the present day field strength is about 50. And each one of these circles is the time average of one dynamo model. So I did 25 dynamo models, and each of them have a boundary condition or a heat flow set by my thermal evolution model. And so let's march actually from the present day back, because I think that's a bit easier to understand. My present day model, of course, produces the right field strength. And the filled in black color here indicates the inner core is the right size. I've got the correct inner core size today. And this little black dot indicates the inner core is tiny, and it's growing over time here. Okay, so over the last 500, 600 million years, when the inner core has been growing steadily, my model predicts basically a flat magnetic field intensity, which is a little bit surprising. But that's because we think the magnetic field has 2 branches, has a strong branch and a weak branch. Strong branch means the energies, the magnetic and kinetic energies are about equal. A weak field branch means the magnetic energy is very weak. So you have a weak field. And prior to the inner core nucleation, it looks like in my models, the magnetic field got very weak. So here, back here, between 600 million years ago and 1 billion years ago, there's no inner core. So we're just relying on cooling. And that cooling rate is very slow at this point. In fact, so slow, the core comes very close to, the dynamo comes very close to dying right here, like very close, right? And the field intensity is weak. And the morphology, I'm going to show you, let's show you right now. Okay, present day, this is an equatorial cut of the temperature. This is what the model looks like. Here's the surface magnetic field, very dipolar, nothing surprising. Right after inner core nucleation, also dipolar. But of course, the inner core is much smaller. Convective structures are different. And then right before inner core nucleation, we have a completely different setup where all the temperature gradients are concentrated near the outer boundary, and the magnetic field is highly non-dipolar. So this would not be a good GAD field. You're not going to get good paleo latitudes or paleo intensities for that matter from a field that looks like this, okay? And then just to continue the timeline here, back before 1 billion years ago, the core is cooling fast enough back here that it was actually back in a strong field dipolar state. So it's dipolar and it's very strong intensity. And then this last regime, which I'm least confident in, is a strong multipolar field. So the reason why I think the magnetic field drops in the models here is because the core is cooling so fast, the convective structures are so small that the dipole is not the favored magnetic moment, not the favored magnetic morphology. It's the quadrupole, octopole, septipole, all the smaller magnetic field components get stronger. So I think what's going on back here is that you have a very non-dipolar field that could fluctuate between strong and weak over time. But like I said, I'm least confident in this branch back here. So we're going to concentrate really on these more recent branches. And here's a movie comparing the magnetic field intensity, magnetic field plots in the model right before inner core nucleation, just to show you how non-dipolar the field is versus the present day field model, which is the one I showed you earlier, which is more or less dipolar, just kind of wiggling a bit around its present day state. I'll say that these models do reverse occasionally. They'll start to deviate so much that they'll reverse polarity, but then they return to their dipolar state. But this one on the left, this pre-inner core nucleation model, is really nothing like a GAD field. It's really just multipolar, very time dependent. Here's another view of what the magnetic field lines look like in a non-dipolar state. So they're kind of all over the place. They're certainly not dipolar. So remember those aurora I was talking about earlier, they would not be near the poles. You would have high energy charged particles raining down at at mid-latitudes, potentially. So it could be bad for life. Okay, so let's put it all together. Again, this is the data. Here's the 1D prediction, which we said didn't fit the data very well. And here's the 3D model. I've just drawn a curve through all of those models to show you the dipole model prediction. And I would say it still doesn't actually do a very good job, right? This solid black line, which is the data, doesn't agree with my yellow or orange line or green. I'm colorblind. I don't know what color this is. Except, in the last 500 million years or so, where it's pretty easy because it's flat. So I published this, but still concerned that there's some things missing here. Oh, this is just to highlight the difference in morphology. So present day dipole, Neoproterozoic, so 500 to a billion years ago, non-dipolar, and then back to GAD, dipolar field, and then non-dipolar again. So sort of oscillating between these states over the last 2 billion years. Right, and so there was a paper published in 2019 that showed some new data I'm about to show you right here that agrees with my model prediction. And so Nature Geoscience asked me to write this perspective, and I spoke about all the other interesting things that are going on in this time period to try and draw some more attention for people to go back and maybe look at the rocks from this time period and try and figure out exactly what's going on. For example, I alluded to this earlier, Africa looks like it's just zooming across the surface of the Earth. Of course, in geologic timescales, this is zooming, right? 100 million years, but these are really fast plate speeds, like 10, 20 times faster than anything we have on Earth today. And the geophysicists don't think that's really possible. So what I think potentially could be going on here is not the Earth's crust wandering around, but the magnetic field wandering around. So these plate reconstructions could be very misleading if the field's not GAD at the time. There's some snowball events during this time frame. I'm going to show you in the next slide. So these really incredible events, we think, with a whole planet iced over, called snowball Earth, same time period. And there's some interesting biological evolution at this time. Okay, so here's all the new data. So the data has been coming in pretty regularly since this study in 2019, this is the new data point right here. So this gets you published in Nature Geoscience. Getting these data points is hard. You have to get a collection of rocks, show that the intensity you measure is robust. And they found this incredibly weak magnetic field intensity at 550 or 530 million years ago up in Canada. And then they sort of drew this very simple decreasing curve, which I wasn't particularly happy with. I reviewed this paper, but nonetheless, it looks like the field intensity is decreasing quite rapidly during this time. So this is about 500 million years ago. Okay, here's another new paper by Lloyd, 2021. Here's the new data here, around 700 million years ago, also extremely weak. Thalner published some extremely weak data points between 600 and 550 million years ago. So again, same time frame. And then the latest one I've seen is by Zhu, 2022, where he published just this dot here and is also showing the Bono data here. So maybe they're seeing a jump in the field intensity, but they think the field is very weak at this point. So the data looks like it's sort of in agreement with the observations. Of course, we still need to fill in a lot of this time frame. We need a lot more data from this time frame in particular, to really pin down what the field's doing at that time and to see if this really is a signature of intercore nucleation. So I still think there's not enough data to put a pin in this, to really hammer it home. But if you ask me, I think this is where we're going to end up putting intercore formation on Earth's history, somewhere around 600 to 700 million years ago. And then I promised I mentioned something about snowball Earths. So the idea is that there are rocks that indicate ice and tropical conditions layered on top of each other in sequence. And that is interpreted as hot, cold, which could only happen if you were in some equatorial region or mid-latitude, and then the whole planet iced over for some reason. And that's where these grayed out regions here, between 720 or 680 and 720. It's called the Sturtian. That's the major snowball event. There's a couple others in the late Ediacaran, the Marinoan and the Glaciers. But these latitudes of these continents where these rocks were formed are paleolatitudes from magnetic measurements. They are assuming GAD field to get these latitudes. So if the field is not GAD, these paleolatitudes are going to be wrong. I can't tell you exactly how. It's just that they're going to be off. And here's another plot showing glacial deposits as a function of paleolatitude. So I think that this really needs to be reconsidered, given that the magnetic field we now are almost certain is doing some weird things during this time. Okay, so that's all I had. And I'll do a quick summary here and then hopefully take your questions for a few minutes. So hopefully I convinced you that the magnetic field is really interesting. It provides a unique window into Earth's deep interior, especially going back in time, right? We don't have paleoseismology. We need to look at what the magnetic field is doing on well-preserved surface rocks. The inner core is a very valuable data point, I would say, for constraining the thermal evolution. The paleomagnetic record still to this day is quite ambiguous. The field of paleomagnetism is not a big one. There's not a lot of people in this field. I wish that it would grow, but it's just kind of fallen out of favor since, of course, Carnegie was way ahead of the game 100 years ago, and then it kind of peaked in the 60s and 70s, and now it's kind of waning a little bit. So hopefully that comes back. The simple 1D predictions, I don't think explain the data, and I don't think they're going to explain the data. I think you have to do this more complicated modeling. I showed you that in the Neoproterozoic in particular, there's predicted to be weak field, non-dipolar, unsteady magnetic field, and that's in fact what people are starting to see in the rock record. Yeah, all of these anomalies here. Weak intensities, reversals, unsettled paleogeography. These are a number of problems that need to be addressed. I question the snowball Earth. I just think more needs to be done to look at these paleolatitudes. And then recently there's been some very speculative papers on if this whole chain of events is true, then maybe this is why mammals evolved to begin with and came out of the oceans onto land, because the land now became more habitable because the solar particles are not raining down at mid-latitudes, they're near the poles. So I've talked to biologists and they think this is a couple steps too far. So I'm not going to advocate for that. I'm not a biologist, but I'm just saying the thought has been published and it's out there. So hopefully more to come in the future on this. And I'll stop it there and take your questions. Thank you.
All right, thank you. We have, so people online can put in their questions at Pigeonhole, but we can also take questions from the room if anyone has them. I'll start with one online where people are gathering their thoughts. So a number of people want to know whether we could get energy, some of this energy for our use that's coming out of the Earth's dynamo or out of the core.
Yes, people use it for geothermal energy, for sure. We're not tapping into the core, of course, we're just tapping into the crust. But yes, there's a continual source of energy there and a nice temperature gradient from which you can do work with in the engineering sense. So not the core, but from the Earth itself, yes, I would say yes.
Were there questions in the room? Okay, why don't, Anna. All right, Anna's gonna bring or Natasha's gonna bring, okay, why don't we start there since they have a microphone?
Yes, these forces from the liquid inner core, they create this really shield that makes life possible on our planet. Is there evidence of this kind of structure in other places in our galaxy, or even?
Well, like I said, all the planets in the solar system have magnetic fields or had them in the past. Mercury and Ganymede are the only two rocky bodies other than Earth that have a magnetic field today. So we think they're 4 billion years old, 4.5 billion years old. So I wouldn't say it's a rare occurrence. Maybe that's like half the rocky bodies in the solar system keep magnetic fields for a long time. And I would put them in that middle Goldilocks zone, right? And what determines where you are on that Goldilocks plot is much more complicated. It has to do with what the mantle's made of, what's the composition of the core, do you have plate tectonics or do you have a stagnant lid? Do you have tidal heating like Io does? So there's a lot of geophysical effects that tell you where you are there, but I don't see any reason why many planets in the galaxy can't. So I've been involved in making predictions for exoplanet magnetic fields, which we've not detected directly yet for technical reasons. But I think in the next 10, 15 years, we'll have some direct measurements of exoplanet magnetic fields to give her some bigger perspective on how common they are.
Question right here.
How about Venus? I mean, it's physically almost a copy of Earth in its size. How much iron is that supposed to have? And can you detail why it's so dead? Because that would seem that maybe that lack of a magnetic field was why it became this burned hellhole, from Dante or something instead of
Yeah.
some tropical paradise that I
Yeah,
read
yeah.
about when I was a kid.
Yeah, no, it's not a tropical paradise. In fact, we can't send magnetic probes to the surface of Venus and look at the rocks because the probes melt. The surface of Venus is 700 Kelvin, 92 bars. So that's 92 times atmospheric pressure. So it's not conducive to making measurements. That's why we know so little about Venus's magnetic history. We do know from probes that it does not have a strong magnetic field today. It could have a tiny weak one that we just can't measure from space, but likely it probably doesn't have one today.
Why not? Why can't you?
So why can't you measure it from space? Because Venus has an ionosphere that's highly ionized and charged and creates its own magnetic field. And we cannot look beneath it without our probes melting. So we're kind of just blocked from Venus's surface.
Doesn't create field lines that you can measure?
If it did have an Earth-like magnetic field, we would measure it. So it doesn't, is what I'm saying. It doesn't have a strong magnetic field. Why it doesn't is a great question that I've spent a lot of time thinking about. I think the simple answer is that it's probably not cooling fast enough. So it's in the wrong side of the Goldilocks zone. It's slowly cooling interior. Why is the interior cooling slowly? Probably because it doesn't have plate tectonics. We think Venus is just a stagnant lid, or just a volcanic surface. There's no subduction. And subduction is an excellent way of cooling the deep interior. So without subduction, you may not get a magnetic field on a planet the size of Venus or Earth. That's the general idea, anyway. Why Venus doesn't have subduction is a whole nother question that I cannot answer tonight.
But he can answer it on another night, so we'll have to invite him back.
Yeah.
I'll ask you another one from our pigeonhole, which is you showed the inner core as being spherical in all of your diagrams. Is it truly spherical or is it bumpy, or how well do we know its shape?
Yeah, it's very close to a sphere. I mean, the Earth is a little squished at its poles from its rotation. And so it's a little bit squished at its poles, but not by much. And then the surface of the inner core, we think, freezes like dendrites, so like the bottom of a glacier. But the scales of those dendrites is probably meters, centimeters. So on sort of a kilometer scale, it's going to be smooth, which is unlike anything we sort of see on the Earth's surface. So it's a bit interesting.
Okay, we have a question over there. Please.
Did the poles switch on the Earth? Did the North Pole go to the south and the South Pole come up? According to, there was a ridge in the Atlantic, which they measured the magnetic things along the ridge.
Magnetic reversals.
And it switched.
Yes. I didn't put that slide in here tonight, but this is the foundation of plate tectonics. Was in World War II, they dragged magnetometers off of Army naval ships looking for German submarines. And this magnetic radar data after the war, they looked at and mapped out what looked like barcodes across the seafloor. Magnetic field that looks like it's vertical, northern, southern, northern, southern, northern, southern. And then they realized that on either side of a ridge all over the world, these barcodes matched up. And that was the key evidence that the Earth's, that the crust is spreading, sort of the continental spreading tectonic motions, and it's cohesive across the whole planet. at any given time, which indicates the magnetic source is the same. So it's the Earth's magnetic field. So simultaneously, we got this information from this data that the plates are spreading and that the Earth's magnetic field has been reversing. So it reverses irregularly every 250,000 years or so. And I could go a whole nother talk on that. But yes, the Earth's magnetic field has reversed thousands of times over its history.
Okay, we have two more questions in the room.
So in your modeling, when do you predict that the outer core and the inner core will solidify? And will that be the moment when life ceases on this planet?
Yeah, that's a good question. So my model predicts about 4 billion years from now, which is similar to when we'll get swallowed by the sun. So it's on one of those death lists, but it might not be the first one to hit us. Yeah.
Thank you. Good question. All right, we have one towards back there. Same question. Okay, well, let me ask one from Pigeonhole while we walk the microphone, which is a related one. You showed that the magnetic field almost died once in our history. If it had died, would it have come back from that death experience? And if
Yeah.
you're wrong about the way that convection is happening in the core today, could it still die on a timescale different than what you just said?
It's a good question whether if it would die, it would come back. I don't know. I think I would like to say yes, but I have not tested that. I think that's worthy of actually doing some calculations. It could have died. I mean, it could have for all intents and purposes, died. And we wouldn't really know, right? There'd just be a gap in the record.
So a related question that's on the Pigeonhole, people are asking whether exoplanets could have magnetic fields, and you already answered yes, there's no reason that they couldn't. But if our convection today is driven by chemical convection, then does it matter deeply what the core is made of in those exoplanets to know whether you can get a long-lived magnetic
Is this
field?
your question or is this off of all
It's
that?
kind of my question, kind of off the.
Yeah, it sounded like an Alicia question. Yes, it matters. It definitely matters what's the composition of the core. It also matters. Well, I'll say why. So if you add a bunch of light elements to the core, like oxygen or sulfur, that core melting temperature drops pretty quick. Pure iron is much higher melting temperature. And so the time at which the core would solidify, the inner core would solidify, changes depending on how many light elements you put in the core. So yes, that matters. Also, the composition of the mantle determines the rate at which heat is pulled out of the core. And that's why that Goldilocks plot I showed you didn't have much detail other than the magnetic categories, because there's so many things that go into the cooling rate of the deep interior and the energetics, really. But yes, ultimately, we want to get there, right?
Okay, go ahead. We have a question in the back.
Hello, my name is Dr. Frank Kelly. I'm the president of the Catholic Association of Scientists and Engineers, and I've been a physicist for many, many years. I have lately become very interested in the problem of the creation being, when did it really be created? I checked with my pastor, and he said you could either have it at 4,000 BC, or you could go with a Big Bang or whatever you want. So I just want to know if, since it's the three major religions all have it at 4,000 BC in their primitive beliefs, I think it would be a good idea if you would run some of those scenarios also when you do your things, so that our little children who have to celebrate Christmas, the coming of the Redeemer, and all that stuff don't get all confused, because you don't have any kind of proof of anything here. And
Well, maybe
and
you can
most
talk
all of
about-
these things don't have any proof of so long ago in
Well,
comparison
Maybe you
to.
could talk
I
about
mean,
some of the
the other
timescales
thing.
involved here,
That's
Peter.
all.
Yeah, like I said, the 650 million year old inner core I proposed is considered young to geologists compared to, the Earth is 4.5 billion years old. We have rocks that are 4 plus. The magnetic field is at least 4 billion, 4.2 billion years old. So 650 million years ago is actually pretty recent on a geologic timescale. Now, if the inner core was so young that it formed, say, a couple thousand years ago, by the mechanism I described here of the core cooling and that intersection point moving out, then you would be able to measure the inner core growing from 50 years ago to today. And that we don't see to the accuracy of the seismology. So I think we can say that it's not that young, but
So do we have any more questions in the room? So I think we can take, and are you up for one or two more questions before we break? Okay, we'll take two more, one here and one here.
Thank you very much for your discussion. It was fabulous. My name is Mark. In one of your diagrams, you had shown where the dynamo had completely almost shut down and died. I think it was 650 million years ago,
Yeah.
but then there was a huge rebound.
yeah.
What was the mechanism that drove that rebounding back up to some higher level?
Yeah, so what the model's doing there is the inner core is first nucleating. And when it first starts to solidify, it rejects those light elements, so it releases some energy. And the first 100 million years of the inner core's life, it's growing very quickly. Okay, just geometrically. Just that temperature intersection with the solidus is moving steadily out in radius, but its volume is growing very quickly. So the actual amount of buoyancy you're releasing is enormous at the beginning. It's almost like a singularity. It's just like very quick. The growth rate's like infinite right at the beginning and then slows down and kind of, you saw it kind of bend over and it kind of flattens and eventually will start to go down a little bit in terms of the buoyancy. So I think that's what's going on there, but people have asked me what is actually going on there. So I think it's worth, this is a kind of a coarse high resolution model, right? This was published in 2016. So I think there's a lot more work to be done zooming in on just what you're talking about. What actually happened at that nucleation time? And can we really pin down in the rock record when that event happened? I don't think we've done that work yet. That's a good question.
Okay, maybe one last question for tonight.
So what's the prognosis for our field over the next so many millions of years?
Our magnetic field. Well, there are many different timescales to the Earth's magnetic field. It reverses every 250,000 years on average, like I mentioned. We're 3 times overdue for a reversal. It hasn't reversed in 780 million years. 780,000 years. It doesn't look like the field is currently going through a state of reversal. People have done sort of forward modeling of the current state of the core, kind of like you do weather prediction, except with the core, they can predict out 50 years or so. And it doesn't look like the field is on its way to reversing. That said, we can't predict, it's a chaotic system, much like the weather. You can't predict it much beyond its forecast length. But in a statistical sense, I would expect the field to reverse again in the next, I don't know, 20, 50,000 years, 100,000 years. And then there's longer time scales where we see when the oceanic plates close, the Atlantic Ocean closes and reopens. This is called the Wilson cycle. We see fluctuations in magnetic field reversal frequency. So it's reversing frequency today, and it wasn't reversing frequently 80 million years ago. So we could also go through an 80 million year, 200 million year cycle in reversal frequency. Those are just some of the time scales, but there's lots of different time scales. So it really depends what question you're looking for. But the field is changing. Like the world magnetic maps had to be redone a couple of years ago because the magnetic field was changing so quickly. And they still use these magnetic field maps for some airports up in Canada and Siberia. And so we do have to follow what the field is doing for navigational purposes, even to this day.
Thank you for coming tonight, and thank you, Peter, for taking us on this journey.
Thank you.
If you registered tonight, you should be on our mailing list for future events, and I hope we'll see you again. Thanks for coming.
How fast does the polarity actually shift when they have one of these magnetic changes?